Just a couple of quick housekeeping things before we do. So one, in the spirit of like all our community meetups, the overall goal here is just learning, right? So we try and keep it pretty informal. If you haven't attended one before, feel free to ask questions in the chat. And when you're presenting, it's kind of difficult to moderate, so I'll try and help moderate the chat. Paul, if I do a bad job at that, maybe you can be my backup and help me, or I guess honestly anybody. If you see me doing a bad job at that, feel free to jump in. And yeah, we'll just keep it pretty informal. I'm really excited for this one. We get a lot of questions just around like, hey, like how should I think about building a claims data platform? And obviously this is something we put a lot of thought into. And Coco and Krish have an awesome presentation to kind of walk through our thinking on this, and how you can use DBT and Tuva to think about this. So I think without further ado, I will hand it over to you guys.
Cool. Thanks, Aaron. Okay, I'm gonna share out my screen and let's kick this off. So, can you guys see this?
Yep.
Okay, I can't see you, so if somebody needs to interrupt, yell out. So yeah, another reminder is just that we are gonna make this recording available for the community, so don't feel pressure to take notes or screenshots, and feel free to kick back and listen and ask any questions you might have. So let's just dive in, because there's a lot of things we want to cover today. We want to share our thoughts today around how to build a claims data platform. So we've built multiple claims data platforms in the past. We've made a lot of mistakes doing that. We've learned lessons. And as a result of that, we have developed opinions. So we want to share some of these opinions today. And before anything, what is a claims data platform? What do we mean by this? So we typically at a high level think of a claims data platform as this big machine that takes raw claims data as an input and it spits out analytics insights as an output. So we basically want to answer questions we care about. What are examples of questions we care about? Things like, what is our spend for type 2 diabetes? What does our ED utilization look like? What is our readmission rate for COPD? These are just examples, but you could easily come up with an endless list of questions that you might want to answer for claims data. And doing this from answering these kinds of questions from raw claims data is incredibly challenging. One of the reasons why it's very challenging is because raw claims data doesn't look like the questions we want to answer. There is no statement in your raw claims data that says your readmission rate for COPD is 8.2%. In fact, what raw claims data looks like is more like this, which is just a bunch of bills with all these cryptic looking codes that are specific to healthcare, things like bill type code or revenue center code or admit type code, et cetera, DRG code. So this looks nothing like the kinds of questions we want to answer. And raw claims data has no concept, for example, of an acute inpatient claim or of an emergency department encounter or of an office visit. And in order to answer even very basic questions, we need to define these concepts on top of the raw data. And we need a whole universe of these concepts. So defining a couple dozen concepts actually gets you nowhere in terms of analytics. And in order to be productive doing analytics, you need more like thousands of concepts defined on top of the raw data to be able to tackle all kinds of analyses. So that's one challenge. Another challenge is that these questions are not precise. So take a very innocent looking question like, what is our spend for type 2 diabetes? The amount of specificity that we need to be able to write a query against data to answer this question is crazy. So first of all, do we mean medical spend, pharmacy spend, total spend? How do we define if somebody has type 2 diabetes? Do we look at the presence of certain diagnosis codes? If so, which ones? Do we look at the presence of certain medications being taken? If so, what are the drug codes corresponding to those medications? Are we talking about the total cost of care for patients with type 2 diabetes, including things like them breaking their arm? Or are we only talking about diabetes-related spend? And if so, how do you define diabetes-related spend in raw claims data? So you can see that you need to define a lot of very specific ideas and concepts just to be able to write a query to answer such a simple question. So we have these two problems. We have the problem that raw claims data is raw and has no concepts to make it useful. And we have the problem of needing to make our questions precise. So the solution to both of these problems is the same solution. The solution is that we need to define concepts using raw data. So we need to define concepts that make the data usable for answering questions. These are concepts like the concept of an ED encounter or the concept of a patient with type 2 diabetes. And we need concepts that make our thinking and therefore our questions precise. So these are concepts like, what do we mean by the total span for condition X? And this concept, for example, could be defined in many different ways. And you might want to have all those definitions available to you in your data platform for answering questions of different kinds. So we know the solution to our problems is defining concepts. There's challenges to doing that. One challenge is that we need a lot of concepts, like I said. In order to be productive doing analytics, you need more like thousands of concepts to be able to answer all kinds of questions. These concepts need to be defined precisely in code. This is typically done by people who write code. And it is a lot of work to translate all these nuanced healthcare definitions into code, ensuring that that's correct, maintaining that over time with changing code sets, with changing definitions. And like I said, these are nuanced concepts that require deep knowledge of healthcare data, knowledge of how medicine is practiced, knowledge of how medical services are billed. And this kind of knowledge is very difficult to come by. In fact, it usually only lives in the minds of certain very specialized kinds of individuals, which unfortunately are often not the same people as the people who write code. So this is where we're at. I'm going to pause here and shift gears for a second, but I want you to remember this because I'm going to come back to this. We have these two problems, that raw claims data has no concepts and that we need to make our questions precise. We know that the solution to this is defining concepts, and there's challenges to this, to doing this correctly. So we'll come back to this in a minute. For now, I want to take a step back and talk about how we all work with data in an organization. So people with different roles and skill sets work with data in any organization. We at least have data analysts, data engineers, data scientists. These are all people that work in slightly different things, but related, and usually work with slightly different tool sets.
Coco,
so
did you stop sharing your screen?
No.
It went away from me for some reason. I don't know. Yeah. Is that just a me problem?
No, it's gone.
It's gone. Let's see.
I've noticed Google Meet has been doing that lately.
Just like randomly, like
yeah.
Just interfering with your work. Yeah. Is that a feature or a bug?
Okay, can you all see this now?
Yeah. It's back. Cool.
Okay, so we're talking about how there's these different data roles in an organization. What does working with data look like for most orgs? We typically have a cloud data warehouse. Sometimes we have more than one. This might sound crazy, but unfortunately, we've seen this over and over in many organizations where there's multiple cloud data warehouses. In situations like this, there's different useful data and the logic to transform that data scattered across different warehouses. And it's very difficult to maintain a source of truth. There's conflicting definitions for similar ideas in multiple places, and nobody understands what's going on. So, but for simplicity, let's just assume that all your data is in a single cloud data warehouse. And there's going to be different kinds of data practitioners querying this data. That they're accessing the data and bringing it into different tools of their choice. So for instance, a data scientist might be querying the data and bringing it into notebook environments or RStudio or Databricks. A data analyst might be querying the same data and then bringing it into BI tools where they're building reports or doing storytelling. A data engineer might be building data pipelines and tools like AWS Glue, writing PySpark code, for example. So everyone is pre-processing data and fixing data quality problems and defining high-level concepts specific for their projects in these different isolated environments. And I'm going to give you an example of a real-world situation that I was actually part of a few years ago. So imagine you have this data scientist building a machine learning model to predict the probability of 30-day readmissions. So the data scientist is querying a data warehouse, bringing data into a notebook environment where they're going to prototype this thing. They're fixing data quality problems on the fly as they find them, the problems that are related to their project. They are grouping claims into encounters because the raw data that they access doesn't have the concept of an encounter built into it. They are defining their own exclusion criteria for these encounters so that they can train their model. They're creating their own 30-day readmission flags to use as a target for their model. Separately, in the same organization, different team, there's a data analyst building a dashboard to investigate readmissions. They are trying to slice readmissions by chronic condition, by provider, by geography, et cetera. Completely separately from the data scientist, they're doing the exact same things. They're bringing data into a different environment. They're fixing data quality problems that they encounter on the fly. They are grouping claims into encounters, defining their own excluding criteria, defining their 30-day readmission flags, unknowingly probably making a lot of these definitions in slightly different ways and maybe conflicting with the data scientist definitions. The data scientist then realizes they're trying to do feature engineering and they want to build chronic condition flags as inputs to the model. So for example, they want to flag a patient to say, is this an ESRD patient? And they want to use that as an input for the predictive model. So in doing some Googling and talking to a clinician, they decide to use the presence of an N18.6 ICD code to flag patients with ESRD. But after doing exploratory data analysis, then they realize that there's a bunch of patients that have this diagnosis code that do not have ESRD and they've never done dialysis. So they talk to the data analyst and the data analyst says, oh yes, I actually ran into this last year. I realized there's this complex logic to identify true ESRD patients. That logic is in a SQL query that's stored in my desktop. Let me share that with you. The data analyst flags the query to the data scientist. The data scientist runs the query completely independently, or even worse, tries to understand it and then rewrite it in Python in the notebook where they're actually doing their work. Is there a single place where all the data lives? Absolutely not. Is there a single place that is a source of truth for all the healthcare knowledge that's being encoded into code? Not in this kind of situation. So when you're in this kind of situation where you have multiple data sources and you're bringing it all into some cloud data warehouse, if you start having different teams and different data practitioners bring raw data into different environments and defining healthcare concepts and logic used for their projects in these different silos, you get into the situation where complex healthcare knowledge is managed in disparate places, and you're going to have different sources of truth, conflicting definitions. It's going to inevitably snowball into this Rube Goldberg machine that unfortunately many of us have seen, where there's very nuanced business critical logic living in complete silos, and it's often contradicting each other. So a much better architecture is to bring all your raw data sources into a single cloud data warehouse and then managing all data transformations in that one place. And so dbt is a perfect tool for doing this because dbt can help you manage all data transformations inside your data warehouse. It's an open source project that helps you write data transformations inside a warehouse. It is basically the T in ELT. T in ELT stands for transformation. dbt is the tool that helps you transform data. And it helps manage the knowledge and the source of truth for all these data transformations in a single place. So I'm going to take a minute to explain something about the dbt philosophy. I want to point out that in practice, these transformations are complex and are often happening across massive DAGs of transformations. So dbt, like I said, is this open source tool that is used to manage data transformations inside of a data warehouse. And it was designed keeping in mind these axioms that describe how they see the world, how the builders of dbt see the world. So axiom number one, code and not graphical user interfaces is the best abstraction to express complex analytic logic. It is easier to maintain complex business critical logic in a single version controlled repository of code than it is to maintain it across multiple GUIs that are being used by different teams. Data analysts should adopt similar practices and tools to software developers, namely working in code repositories that are under version control. Axiom number three, critical analytics infrastructure should be controlled by its users as open source software. And axiom number four, analytic code itself, not just analytics tools, will increasingly be open source. Obviously, this fourth axiom completely resonates with the Tuva philosophy and religion. We strongly believe that all healthcare analytics codes defining the concepts that we all use as an industry will increasingly be open source, and we will be sharing that as an industry and refining that as an industry. So this is an opinionated philosophy for how to work with data. It's gaining massive traction in every industry. Obviously, healthcare is not an exception. And one nice thing about this is that people who are very close to end use cases are managing all of this knowledge in one place. So in contrast to that, let me share another quick story of the data platform that I was actually part of building some years ago. In this situation, we had multiple data sources being ingested from different data providers. We were each data source was landing into its own separate location in cloud storage. And all data sources obviously have different data models, different column names, different vocabularies. They have their own data quality problems. So we had this team of software engineers that are, they're not people responsible for building end applications. These are not people who will ever build a dashboard or a report or a predictive model. And so this team of people was writing Spark jobs to transform all these raw data sources in different formats into a common data model. And in doing that, they're managing all these definitions of healthcare concepts like chronic condition flags inside of PySpark code to transform all these raw data sources into a common data model. Just imagine trying to deal with doing claims adjustments and denials and reversals inside Spark code. If you're a software engineer who's not doing healthcare analytics usually, it's obviously a very bad idea, but believe it or not, this is what we were doing. We were transforming all these raw data sources into a common data model in this way and dumping all of them into a different location in cloud storage. Obviously, this is riddled with problems we're not even aware of. Then we load it all into a cloud data warehouse from which different data practitioners and different data teams are querying the data and bringing it all into different tools, all these different silos. And inside each of these different environments, people are defining business critical logic and important healthcare concepts, often in contradictory ways and in a way that's not conducive to cooperation. So the knowledge lives everywhere. Nobody knows what's going on. It was a very, very bad situation. Instead, we later switched to this. We basically threw all our Spark jobs in the garbage can. We restarted. We built a data platform with a single data warehouse. And we brought in all our raw data in its raw form into the single data warehouse. And then data scientists and data analysts were responsible for all data transformations, starting from the raw data. These were the people who were in touch with the end applications of the data, who were most familiar with the concepts that needed to be defined for their projects. And so they were owning all data transformation. They were managing it all in the data warehouse through a DBT project. And then software engineers and data engineers changed their focus to making sure that all the raw data was readily available in the data warehouse and always refreshed on time for the data scientists and data analysts to consume in its raw form. The tool that was used to manage all the data transformations was DBT. And in this scenario, all transformations for all data sources happen in one place, namely inside of a DBT project, which is a repo under version control. And all the data transformation that's happening for analytics is happening as SQL select statements inside of this one version controlled repository. So conceptually, this architecture makes sense. When we switched to this, everything was better. But we still have this problem of having to define thousands of healthcare concepts on top of the raw data to make the data useful for answering questions. So I said I was going to come back to this. We said a claim data platform was this machine that takes raw claims data and turns it into analytics insights. We said that we have two problems, that raw claims data is raw and has no concepts, and that we need to make questions precise. We said the solution to those problems was defining concepts, and there's challenges to doing that. So I want to dive a little more into the big challenge of why this is difficult. So when we have multiple data sources, they inevitably all have different schemas. They all have different field names. Even for standard fields that are present in every single claims data source, like bill type code, they're often going to have completely different names in different claims data sources. They have different vocabularies. We often see things like place of service codes being custom in a claims data source, and they need to be crosswalked to standard national values that we're all going to use. And then obviously we all know that raw claims data can be modeled in many different ways. You can model raw claims by having a claim header table and a claim line table, and then you have some logic to join these tables to extract all the data that you need. You could model claims data by having a table for inpatient claims, a table for outpatient claims, a table for DME claims, etc. This is, for example, how CMS models LDS data. If you ever buy that data set, that's the form you're going to get it in. You can model claims data by having just a very large medical claim file at the line detail level, where you have all medical claims, and you can do the same thing for pharmacy claims. So if you have all these different claims data sources, we have to model all our raw claims data sources in the same way. For this, we need a common claims data model. If you have a common claims data model, all your claims data sources are modeled in the same way, and then they can be unioned, and then you're comparing them in an apples to apples way. But if we do this successfully, we still only have raw claims data. So We said that to answer even the most basic analytics questions, we need a whole universe of high-level concepts defined on top of the raw data. So from your common claims data model, if you succeeded in putting all your raw sources in a common data model, at the very least, you're going to need to build a service category grouper. You're going to need an encounter grouper, an episode grouper. These kinds of ideas pre-process claims into useful concepts that are going to be used in many different analyses. You're also going to need atomic data concepts that are not present in a raw claims data set. Things like the concept of a patient or the concept of an encounter, the concept of a condition or a procedure, things like the concept of a location or a medication. These are all core concepts that are common building blocks for almost any analysis anybody would do. And then on top of that, you also need to start defining data marts with more high-level concepts. So for example, you might want a chronic condition mart where all the logic for identifying which patients have which chronic conditions, what are the diagnosis codes or the medications needed to specify the presence of a chronic condition. All that logic could live in a mart designed to answer those kinds of questions. Similarly, you might want a financial mart where concepts used in financial analytics are defined and organized. Similarly, you might want a readmission mart where all the concepts are organized that would help you do readmission analytics. And the same thing for emergency department analytics or for HCCs or for HCC suspecting. So you have to have this large collection of marts with higher level concepts that are frequently used across many different kinds of analyses. So these are just examples to give a flavor of how large the universe of concepts to build actually is. And these are not anyone's secret sauce analyses. These are just table stakes that we all need just to be able to start doing basic analytics. And for years, we have all been reinventing the wheel and redefining these concepts in isolation inside the walled gardens of our own companies. We're all defining these concepts in slightly different ways. We're all introducing our own bugs and problems to our definitions. And the concepts are not getting refined and getting better because we're all starting from scratch, doing them over and over again. We're not improving them together as an industry. So this was the motivation for us to start the Tuva project. When Aaron and I started Tuva a few years ago, our vision was to have a common data model that we could model raw healthcare data in, and then could build a DBT package that could run on top of that data model, and it could produce this entire universe of concepts and organize them into marts that make sense and that are useful for analytics. And so this common data model to model the raw data plus the data model of all these data marts is what became the Tuva data model. And so we built this Tuva DBT package, and we built this to run on all major cloud data warehouse. And that was the start of our Tuva adventure. Over time, the universe of data marts got bigger. It is something that we've been working on full time for the last several years with the Tuva team. And so this universe of concepts is continuously expanding and getting more refined. It's obviously all open source, so people from the community can contribute to defining new concepts and to refining the concepts that are already there. We've also gotten feedback from the community about how running data transformations inside of a data warehouse at scale is very expensive. We've responded by building a Tuva enterprise version that runs in a container outside of your data warehouse, and this results in 90% cheaper compute cost than running it inside the data warehouse. But over time, the Tuva project grew into something larger than the Tuva data model. So now the Tuva project is this large universe of open source tools that are needed to build the healthcare data platform. These are all the tools that you would need to go from raw data sources all the way to insights. And the Tuva data model is still the heart and soul of the Tuva project. All the other tools in the Tuva project are designed to work in harmony with the Tuva data model. So for example, we have Tuva EMPI, which is a standalone patient matching application. This is designed to work with the Tuva ecosystem by creating universal person IDs that propagates to the analytics layer. But this application can be used independently of the rest of the Tuva ecosystem. In fact, there are examples of companies that are using this application and they have not adopted any other tools in the Tuva project. Similarly, for terminology sets, this is a collection of commonly used healthcare terminologies, things like ICD, DRG, low-link, etc. These terminologies, you're going to need access to these terminologies to do analytics in healthcare. They are maintained by many different organizations. They are updated at different frequencies. They're scattered all over the internet. It is incredibly painful to get all of them and have the latest version of all of them in your data warehouse. So through our Tuva terminologies, we make it possible to just have the latest version of all terminologies in a push button kind of way inside of your data warehouse. Also, some of these terminologies in their raw form are actually pretty hard to use, and non-trivial transformation needs to be done on top of them to make them into a more useful form. But these are things. This is something that could be used completely independently of the rest of the Tuva ecosystem. And there also are examples of teams that we know of that are using Tuva terminology without using any other tools in the Tuva project. There's other kinds of tools like data quality testing or analytics, notebooks, and dashboards or predictive models. These kinds of tools are different because these are tools that run on top of the Tuva data model. And so having your data in the Tuva data model is a prerequisite to using these tools because the tools are going to use concepts that are defined in the Tuva data model. Then we have connectors. So connectors are data pipelines that get your raw healthcare data sources into the Tuva data model. So remember, the Tuva data model is this common data model for modeling raw healthcare data. This is what we call the Tuva input layer. It just models all your raw data sources in a common way. And then we have the data marts that are built on top of the common data model for raw data. So you get all of these data models for free if you have your raw healthcare data in the Tuva input layer, because the Tuva DBT package just creates them out of the box. But if you have multiple data sources that you want to get into the Tuva data model, you need to map each of these data sources into the Tuva input layer. And doing that requires a connector for that data source. So a connector is just a data pipeline that maps a particular data source to the Tuva input layer. So for example, in this diagram, if that's the situation you're in, you would have a connector to map this particular claims data source into the Tuva input layer. You would have a different connector to map a different claims data source into the Tuva input layer. If you wanted to map the back end of your EHR system into the Tuva input layer, you would use a separate connector for that. And if, for example, you had a fire feed that you wanted to also map to the Tuva input layer, you would use a separate connector for that. So each connector is just a DBT project that maps that healthcare data source to the Tuva input layer. And in that DBT project, you may import the Tuva DBT package so that when DBT runs, you not only map your raw data to the Tuva input layer, but you also get the Tuva package to build the universe of data marts on top of your raw data. So there's pre-built connectors. We've been building out a bunch of connectors for standard healthcare data sources that are common to many organizations. We've built connectors to very commonly used medical record systems. We've built connectors to commonly available FHIR sources. We've built connectors to some standard claims data sources. These are all DBT projects that map these particular data sources to the Tuva input layer. And if you have data from one of these sources, you could use one of these connectors and just map the data straight into the input layer. But you need custom connectors if you have data in a format for which we have not built a pre-built connector. So if you have data in some arbitrary format, you need to build a DBT project that maps that data source to the Tuva input layer. So there's a distinction between these pre-built connectors and custom connectors. Now I just want to summarize the main ideas of what I said before we switch gears and jump into a more hands-on demo of building a connector. So first of all, we said that a claims data platform is a machine to go from raw claims data to analytics insights. We said that if you're in a situation where you're ingesting multiple data sources, you want to avoid this Rube Goldberg situation of having critical business logic defined in many different silos. This becomes incredibly difficult to manage. And we said that a better way to do this is to have all the data transformation happen inside of a single data warehouse within a single DBT project, or it could be done with multiple DBT projects, but it's managed under version control in a single data warehouse. All the transformations here happen as select statements in a version control repository. It's much easier to manage. But if we're doing this, you still have the problem of having to build this very large universe of healthcare specific concepts. We've spent north of 50,000 hours building the Tuva project. So it's a lot of work to build such a large collection of healthcare concepts. And then maintaining this over time requires a tremendous effort from people with very specialized skill sets, because you're managing a large universe of interdependent concepts over time with changing terminologies, with changing definitions and changing code sets. And it's a lot of work. So this is what the Tuva package does. The Tuva DBT package is managing all this knowledge. It's an open source package that we want to collaborate on as an industry so that we can all use the same concepts as an industry and keep refining them over time. But in order to run this Tuva DBT package, you need to have all your raw data modeled in a common data model. that is the data model that we call the Tuva input layer. And in order to get your data in the Tuva input layer, you need to have connectors that can map these different data sources into the Tuva input layer. So this is the summary of the main idea for why we need a connector. Now we're going to switch. I'm going to shift, or we're going to let Krish talk about the specifics of how to build a custom connector. We talked about how we have pre-built connectors that you could just run automatically if you happen to have data in one of those formats. If you don't have data in one of those formats and you want to put your data in the Tuva data model, you need to build your own custom connector. So Krish, I'm going to hand it over to you and let you talk about building a custom connector.
Thanks, Coco. I've just got a few more slides here. Thanks, Coco, for an awesome introduction to kind of DBT and why Tuva. You'll have to let me know if you can see my screen, and just feel free to interrupt me anytime. Can y'all see this okay? Awesome. Yeah, so it's like Coco was saying, a connector is a DBT project that maps a raw data source to the input layer, and it's what enables the Tuva data model as well as all of the downstream analytics. So I want to kind of zoom in a little bit on what it's like to map a data source and some examples of logic and transformations you'll need to write. When we're mapping a data source in this DBT project, we are doing logic and transformations that you need to standardize your data. And the reason we need to standardize your data is to enable the Tuva data model to work. There is logic inside of the Tuva DBT package that depends on specific inputs. And building a connector is one of the ways that we ensure that those inputs are what Tuva is expecting. So one example of that is if you're looking at 3 different raw data sources, your claim ID and your claim line number might be represented in different ways. And as you're mapping to Tuva, you need to make sure that you're unifying basically a bunch of different raw sources into expected column names, expected data types, and expected formats. Another example here, for different diagnosis codes, we accept a couple of specific types, ICD-9-CM and ICD-10-CM, and it might be represented differently in your raw data. Again, you need to unify the inputs at the Tuva input layer so that your data looks like this, and then the Tuva data model can run and you get access to all of these downstream analytics. I've got just a couple more examples here. And we've also kind of refactored some of our documentation. There's a field level claims mapping guide that walks you through how we think about mapping each column that you'll need to in your raw claims data to the Tuva input layer. When you're mapping a data source, we kind of assume that your data has already landed in your data warehouse. And during that process, if an extract from a carrier got entered into Excel at some point, leading zeros often get truncated or cut off. And so you want to make sure that you're adding those back in at the Tuva data model at the input layer to enable all of the correct analytics. So I just want to run through one more example. We expect one claim start and end date per claim, which can require aggregation to the level of a single claim ID. You might have a claim that looks like this, where you've got a start date and an end date specific to the specific line of the claim. And we want to keep that information, but then also aggregate it up to the level of the claim ID. So just wanted to walk through a few examples here of some of the more granular data transformations you'll need to do before the Tuva input layer and in your connector. I think Coco talked before about the pain of running and writing adjustment, denial, and reversal, or ADR logic in Spark. And I wanted to call out that it's an expectation at the input layer that you've handled adjustments, denials, and reversals for your claims in your specific mapping process, because ADR can look really different across a lot of different claim sources. And I also want to call out that we could probably spend another hour talking about ADR. So for the purposes of our talk today and this demo, I think we're going to say maybe we'll talk about ADR in the future, but we're not going to talk about it today because it's probably like a gas and it'll just expand to fill whatever container we give it. And I also wanted to highlight some of the documentation that we've got on our site on ADR. Encourage you to check that out on our knowledge base. So thanks to Coco and hopefully this quick overview, we now know that a connector is what sits between your raw data and the input layer. And I want to spend a little bit of time walking through a connector template that we've put together that we hope makes it easier for you to get started building your own connector. And then again, highlight a claims mapping guide that we've put together as well. So with that, I'm going to switch over to a demo here of how you can get started building your own connector. And we can, well, I guess before I do that, are there any questions? I think we've got a little bit of time here before I can get started with the demo.
No questions in the chat, but Sarah's excited for a live demo.
I'm excited too.
That just makes it interesting.
Yeah. All right, let's get started then. So. Can you all see my screen?
Yeah.
Yep.
Okay, great. So we've got a DBT project that we put together that's a template repository on GitHub. It's got some of the building blocks you'll need to get started building your own connector. One of the things we really like about this template is that it's very easy to create your own GitHub repository from it.
Hey, Chris.
You just, yeah.
Sorry to cut in. Yeah, can you zoom in just a little bit?
Oh yeah, for sure. Is that better?
Yeah, maybe one more click for those of us with bad eyes. Thank you.
Of course. Thank you for saying something. Cool. So it's pretty easy to create your own GitHub repository from the template. I'm just going to walk through that process here and talk you through some of what you'll need to change and alter to get started specifically building your own claims connector. I'll just create a new repository. I'll put it on my GitHub account. I'll call it my connector. I will make sure to tell the world this is a test. And then I can create my own repository with a single click. And one of the nice things about a template is that you get access to all the files that ship with the template with their own independent Git history. So if I were creating my own project here, I'm just initiating a repository that's got all of the necessary components to build a claims or a clinical connector with a single commit. And so if I wanted to pull this down and make some changes locally, I would open my terminal. I'll make sure I'm zoomed in. I'll git clone this repository. I'll set my directory to this repository that I've just cloned. And I can just take a look inside here and I can see that this looks like a DBT project. It's got all the files that are available in the template. And I'm pretty much ready to start making changes to this DBT project so that it kind of fits my needs depending on the data sources that I'm using and the kind of connector that I want to build. So I think a next step here would just be to open a code editor and kind of walk you through some of what you'll need to change. Again, making sure that I'm zoomed in enough. Let me know if I'm not also. I think, oops. Okay, maybe that's a little bit better.
Yeah.
Cool, thanks, Paul. So a good place to start is your dbt project.yaml file. There are a couple of different things you'll want to look at here. The main one, or I guess one that I want to change right away is I just want to change the project name so that's the same as my connector, and then same here. And then there are a couple of uncommented variables in this part of the dbt project.yaml file. I think the main one we want to consider right now is whether we're building a claims connector or a clinical connector. That variable is basically what tells the Tuva input layer what tables to expect. So right now we're going to focus on building a claims connector. So I'll uncomment this, save my project.yaml file, and then I'm pretty much set as far as changes that I need. So then the next step here, I would step into the models directory. We've included with the template basically all of the different possible input tables that the input layer would expect. Depending on if you're building a claims connector or a clinical connector, those expected tables will be different. And because we're focusing on a claims connector, we can delete everything that is not eligibility, medical claim, or pharmacy claim. Delete that. And then something else I'll do, there's some testing written that ships with the connector template for basically all of the input layer tables. Because we're building claims connector, I can delete the testing that's for non-claims tables. And then just to give some depth to the example that we're walking through, you'll often be sourcing in your raw data. DBT has a source command where you can effectively import your raw data in a staging model. So I guess I skipped over something that I want to make sure I address before we source data. You'll see 3 directories that ship with the connector template in the models folder. We've only included models in the final directory. And right now the models are just select statements that create empty tables. In the intermediate and staging directories, we're expecting that you're writing the logic and the transformations to handle some of the examples that we walked through, and then at a higher level to do the task that Coco was describing of going from raw claims data to an input layer format that enables the Tuva data model when you run the whole project. So what we'll need to do is we'll say, okay, we've got our source data coming in from somewhere, and I've actually created some sources using fake data here. So let me add that in. They're in a schema called my raw data. And then what we'll do here is we'll actually just create select statements at the levels of eligibility, medical claim, and pharmacy claim. And then we'll just do this. Cool.
So here, obviously, depending on how different your raw data looks from the input layer, this could be building a custom connector could be a matter of minutes to a matter of many hours of work and doing very sophisticated transformation logic. Here, this is a limit of just you're doing select star transformations.
Yeah, this is the fastest I've ever built a connector, actually.
Yeah.
Setting a new record. Yeah, so thanks, Coco. One other thing I want to kind of walk you through here is how you'll actually get started running DBT. With this connector, we've included a requirements.txt file, and it's pretty bare bones. We're including DBT core, a specific Snowflake adapter. We're using Snowflake for this demo. Depending on your setup, you might need to change the adapter that you're using for your development. And then we've also included a linter, which has customizable rules. You can get rid of the linter if you want, but these are just kind of the Python packages that we're including with the repository. And so in order to actually, yeah, go ahead,
At the
Paul.
risk of exposing my ignorance, I didn't originally know what a linter was until someone on the team explained it to me. So would you just give a quick, like, what is a linter?
Yeah, for sure. A linter is basically a set of configurable rules that you can run lint or fix checks on your code to make sure that it's formatted consistently according to the expectations.
Thank you.
For sure. Cool. So I'm still in my.
Chris,
Sorry,
we
go ahead,
have a
Aaron.
question in the chat.
Yeah.
What types of transformations are typically seen in connectors? I see case when statements, but wondering what the other common transformations would be. What are some of the most common transformations you've seen, Krish? You went over some of them at in your earlier slides.
Yeah.
Like renaming columns for things.
Yeah. So I'd say it's a few things. It's like you're saying, Aaron, you're making sure you're taking column names to the column names that are expected by the Tuva input layer. You're doing a lot of data typing. There are specific expectations the input layer has around specific data types for things like allowed amounts or paid amounts, wanting to make sure that those aren't formatted as characters, and trying to avoid issues effectively coming up like with something like that. There are a couple of other different expectations that the input layer has. I think Coco went over data quality and DQI, which is a set of, I think it's over 600-ish tests that come along with the Tuva project that evaluate your data, kind of ensuring that it's in the correct format. And some of that is expecting diagnosis codes to be format a certain way, because if you've got diagnosis codes that don't match regular expressions that we expect them to, maybe they're not valid diagnosis codes. And then I guess if I would be remiss not to mention ADR, even though we're not talking about it today, I'd say if you're building a claims connector, a lot of the logic that you're writing will depend on how adjustments, denials, and reversals are represented in your raw claims data. And then for clinical connectors, there are a lot of different transformations you'll need to do. And some of them are making sure to recognize, like, often there will be like a code field in an encounter table, and you need to write some logic to understand what code it is. Like if it's a LOINC code, SNOMED code, something like that. So that was a long-winded way of saying there are a lot of different kinds of transformations you'll need to write in your connectors, and it's kind of data source dependent, if that's helpful.
Yeah, I mean, the one kind of transformation that you're probably not going to be able to get away from is renaming fields, because inevitably you're going to have fields that are named differently. If you're really lucky and your raw claims data is modeled very similarly to what the Tuva input layer expects, then you're mostly just doing field-to-field mapping. But you might have to create a field in the Tuva input layer by combining two fields in your raw data or something like that. So you might need more sophisticated logic depending on what your raw data looks like. And like you said, Krish, getting into doing adjustments and denials and reversals, that's probably the most hefty kind of transformation that you would do.
Right. I know we're running short on time here, so I'll just zip through the last bit and we can use the rest of the time for questions. Let me spell Python right. So basically what I want to do here is create a virtual Python environment, install the requirements, and then show you what you need to do to run DBT. So I've created a virtual environment. I'm going to activate it. And then I can pip install the requirements. So this also assumes that you've configured a profiles.yaml file, which is a YAML file that you use to make sure that you can connect to DBT from your local environment. And I just want to make sure that I am good connected to DBT so I can run DBT debug. Looks like I'm good. Cool. And then I want to install my dependencies, and the Tuva project is specifically one of my package dependencies for this connector project. And you can see that it's being installed here. And then because we've kind of gone through this lightning fast process of building a connector, I can just run dbt build, and that will go from my raw data, do all the mapping logic that we've put together in this connector, and then it will run the Tuva input layer, making sure that my data is in the core data model, and then it will effectively spit out all the data marts that come with the Tuva project. And this will probably take a couple of minutes. I've done this before the demo so that we can look at the end result, but kind of before we do that, I want to make sure that there's time to address any questions.
There's one question from Apollo. Are there incremental load features like metadata for loaded and unique keys to match current versus updated records?
Yeah, so on this one, I think currently we do not support incremental loads with the Tuva project. Coco or Aaron, you all might have more to add there.
Yeah, it's kind of a tricky thing because even in the mapping of the, all the way upstream of the DAG, there's kind of like aggregation that's happening where we're looping over records. For example, with ADR, you're comparing records. And so even as you add new data, your ADR logic might need to run against your previous claims to kind of do a comparison. And so anytime you're doing that sort of thing, where you're grouping data, it makes doing incrementals. If you have new data coming in and that new data needs to somehow be grouped or compared to the prior data, it makes doing incrementals pretty difficult. One of the things that you can do is DBT gives you pretty fine grained control over what parts of the overall DAG that you run. So DBT has something called selectors where you can kind of rerun different parts of the project. So I guess in summary, there's nothing that enables incrementals out of the box today. We're thinking about how to enable that. For example, you probably would have some logic that says, hey, after a certain period, don't adjust any prior claims or something like that. And so maybe we can build that in, but even up to some point in the project, like where we're computing quality measures or readmissions or something like that, there's actually no good way to do incrementals because you have to loop over all the data. So it's kind of it's a good question. It's kind of a tricky
that is something that we've been very interested in, thought a lot about, but we just haven't, like Aaron said, there's those challenges with computing something like a quality measure that makes it very difficult to do this. So if anybody has any good thoughts on that, definitely reach out to us.
We have another question from Jason. At what point are you dropping records if there are bad codes, or do you just null that field within the record or something else?
Yeah, so for example, if there's let's say a diagnosis code and a claim that's not a real ICD-10 code, that code would be propagated through the project, but in the core tables, you have the raw value for your code, and then you have a normalized value for your code. The normalized value for that code would be null because there is no normalized code that corresponds to that fictitious ICD code. So you can see in your core tables what are your raw values that you had in your raw data set, but then if there's no normalized values corresponding to those, it means that the code was fictitious.
One thing before, Chris, you jump in and show us the results. If you're struggling or working on building your own connector and you have questions, or if you have questions about anything related to the Tuva project, we have sort of adopted like an on-demand office hours, and we have a calendar for that. I'll drop a link in the general Slack channel. So feel free to grab time with us if you just want to go a little deeper and more specific to your use case. And sometimes that's the best way to talk through some of the nuances.
And obviously there's a little bit of getting up to speed required with DBT. DBT has some really good quick training demo stuff that you can walk through that shows you the basic fundamentals of like running, creating a DBT project, connecting it to your data warehouse, running it.
Cool. I'll just wrap up here, and then we can, if we've got time, this should take like a minute, and then if we've got additional time, we can take any more questions. All right, can y'all see this all right?
Yeah.
So one of the nice things about the Tuva data model is any query written against the Tuva data model can run against the Tuva data model on your data warehouse, no matter, essentially, if we at Tuva wanted to understand what chronic PMPMs looked like, we would write this query. And then if you've adopted the Tuva data model, you could come to our docs site find this query, run it, and use effectively the same logic, because you've used the same logic to build your tables. You're using the same business logic to understand what chronic PMPM spend looks like. And so I just want to take this query, run it in Snowflake, and then I can just show you effectively the output here. So we're just looking at fake Medicare CCLF data. We've got chronic condition categories. We're looking at medical PMPMs. And this is basically one potential application of how you go from raw data to building a connector to running the whole project, and then having the ability to kind of like answer an analytics question.
Chris,
So
maybe
I'll
just hop back to the tuvaproject.com real quick and go to the connectors section and show people the pre-built connectors section is or sorry, not the pre-built, building the connector section. Yeah, the pre-built connectors section are like the connectors that we've already kind of built. Like if you have Medicare CCLF data, there's a connector for that. But if you're building a custom connector, these docs walk through that. And like Krish mentioned, the claims mapping guide kind of walks through some of the nuances of the heuristics or rules of thumb for how you do this stuff. And then on the knowledge base is the ADR kind of guide to doing 80 adjustments, denials, reversals that Chris showed in the slides. So this is all out there, but if you're like, Paul was saying, if you're building a connector, you're having problems, post something in Builders Ask, and we're also happy to jump on the phone. So, but this was great, Christian Coco. Awesome. Awesome presentation. So thanks for walking through all this.
Yeah, thanks everybody.
Thank you all.
All right,
y'all.
we'll leave it there. See you guys.